Hello. After the discussion of semaphores, here we will discuss the second important concept called monitors. So what will be covered in this unit? We will talk about some historical remarks and the basics of a monitor. Then we will investigate the concept and the use of condition variable through two methods, weight and signal. And then from the interaction between weight and signal, we distinguish two types of monitors, the Hoare type and the Mesa type. Then we will explain to you several examples. Through this example, you'll learn how to use monitors and condition variables. Then we talk about several important things. Because we have two types of monitors, the Hoare type and the Mesa type, what are the differences between the Hoare type and the Mesa type? And then we compare the differences between semaphores and monitors. We will also mention how to simulate monitors using semaphores. And finally, we'll explain how to program monitors using ThreadMentor and its visualization. The concept of monitor was invented by Per Hansen in early 1970s. During that time, Hansen received a master's degree from the EE department. He was working on some operating system projects. And he found out that the concept of class developed in a language called Simula 67. Simula is a simulation language. It's not today's object-oriented programming language. But anyway, the concept of class came from Simula 67. From the concept of class, Per Hansen was able to define the shared class. That's the beginning of today's monitor. Then Tony Hoare, and you know this name so many times in this class, refined Hansen's work to become today's monitor in 1974. Per Hansen is also considered as a pioneer of concurrent programming. He designed a language called Concurrent Pascal, in which all synchronization is done using monitors. Here are the landmark or seminal papers about monitor. And here are several important landmark publications. The first one was written by Per Hansen, Operating System Principle. The first book, written in a very concise, very clear way, in which concept of monitor was discussed and explained. And Hoare's paper was published in the Communication of the ACM with the title, Monitors and Operating System Structuring Concept. Now, you know this. The concept of monitors came from operating system. And then Per Hansen, when he was with California Institute of Technology, Caltech, direct Alfred Hartman to develop a compiler for mini computers, a PDP 11 computer. This is Hartman's PhD thesis, a concurrent Pascal compiler for mini computers. And in 1977, Hansen's another landmark book, The Architecture of Concurrent Programs, appeared, in which the concept of monitor and its concurrent Pascal were clearly defined and discussed. Our library should have these books available if you are interested. Then we're going to explain what is a monitor, some basic concept. Monitor is a very highly structured programming language concept, actually after the development of semaphore. People were looking for a more structured programming language construct. Approximately at the same time, the concept of structured programming appeared. Therefore, it's not a accident. While a group of researchers studied how to write structured program, the concept of structured program was also applied to concurrent programming. So a monitor in today's point of view is just a structured programming language construct, a class, for example. It consists of the following three items. The first one is a set of private variables and a set of private procedures. Private variables and private procedure can only be used inside a monitor. And some constructors, these constructors are used to initialize the monitor. Then we have a number of public monitor procedures. So monitor procedure can be private or public. Private procedures can only be used inside a monitor. You must be executing in a monitor in order to use these private items. But the monitor procedure, the public ones, can be called by any user outside of a monitor. So the communication between a monitor and the threads that monitor support must go through monitor procedures. Look here, monitors do not have public data for protection purpose. So if you like some comparison, you may consider a monitor as a mini operating system. Inside an operating system, you have so many data structures like the PCB and so on. Those are private variables. And of course, inside an operating system, you also have many procedures to be used by the procedure inside the operating system. But you have no way to access the private data inside the operating system. So a monitor is just a mini operating system. But what are these public monitor procedures? Well, simply put, they are the system calls. When we need something to be served by the operating system, you call system calls. By the same reason, a monitor is designed to serve threads or processes. So when threads or processes need help, they simply call the public monitor procedures as if they are calling the system calls of a operating system. So this mapping is natural, and actually this was the original idea. as described by Brubringshit Hansen. Now, there are some very important things you need to remember. In a monitor, there is no more than one process that can be executing in a monitor. Look here, executing in a monitor. That means at any moment, there is no more than one process or thread that can execute instructions or execute statements built into the monitor. Those statements may be private monitor procedures or private or public monitor procedures. So the monitor guarantees you the mutual exclusion property. That is, at any moment, there's only one process that could be executing inside the monitor. So isn't the monitor itself is a critical section? Yes, of course. So how do we implement this? When a process calls a monitor procedure and enters the monitor successfully, you call the monitor procedure, and if you are successful, you execute inside the monitor, and you are the only process executing in a monitor. But what if when you call a monitor procedure, someone is already executing inside the monitor? In that case, the monitor will not allow you to enter the monitor because someone is already there. And due to the mutual exclusion property, if someone is already executing in a monitor, you cannot enter. So you wait outside of the monitor, as if when you try to enter a critical section but could not enter, then you wait outside of the critical section. So here, important concept, the mutual exclusion concept of a monitor. At any moment, there's no more than one process that can be executing inside a monitor. When a thread or a process calls a monitor procedure, if someone is already executing inside the monitor, the caller will be blocked outside of the monitor due to the mutual exclusion property. And if when that process or thread calls a monitor procedure and there's no one executing in the monitor, then this caller, a process or a thread, depending on the system, will be allowed to execute inside the monitor. So in this case, the caller of that monitor procedure start execution of the procedure's statements. And this implements the mutual exclusion requirement of a monitor. So here is a diagram showing to you the concept of mutual exclusion. We have a monitor. This monitor has some initialization procedure, the constructors. And the monitor has some private data. It has no public data. And a set of monitor procedures, some of them may be public, some others may be private. So when a thread or a process calls a monitor procedure, and if someone is already executing in the monitor, the caller will be blocked outside of the monitor. So just like processes or thread that are blocked by a mutex or a semaphore, we really don't know, and we should not assume any ordering. So the blocked threads or process just form a set, an ordered set. So when someone who was in the monitor finished is execution. So the monitor becomes empty. So that thread gets its control, returns from a monitor procedure. Once that happens, monitor becomes empty. No one is there. Just like the critical section issue. When someone exits, the mechanism of the critical section must allow a waiting thread to enter. By the same reason, when the only executing thread or process in the monitor exit, the monitor becomes empty. The monitor mechanism will find a process, a waiting process or a waiting thread to enter. But what if there's no one waiting there? Well, the monitor is still empty until the next caller to come. So this explanation of the mutual exclusion of monitor is exactly the same as the mutual exclusion for a critical section. Then we will write several examples in the next few lectures. So let's agree upon the syntax here. This syntax is, of course, not corresponding to any existing programming languages. So here, we write it in a C or C++ like syntax. We start with monitor, followed by a name we assign to a monitor. We have some local variable declarations. Always remember, all variables are private. Think about why. And we have a set of procedures, public or private. So at the end, we have a pair of curly parentheses. We have all our initialization here. So these are the constructors. So these are very simple syntactic rules for you to remember. Now, let's take a look at a very, very simple example. Remember, when we maintain a counter, some thread may increase it, some other thread may decrease it. So the increment and decrement operation must be protected by a critical section. Now, if we know monitor, this is very easily done. Let's write a monitor. Let's call it ink deck. The counter to be protected is a private variable count here, and initialized, and it's initialized to 0. We have 3 procedures: increase, decrease, and get data. The increase procedures add 1 to the counter. The decrease procedure subtract 1 from the counter. The get data procedure returns the value of count, the current value of count here. So a process that keeps increasing the value would be something like this. Use the dot notation. This process calls the increase procedure of the ink deck monitor. So add 1 to the counter, and then calls the get data procedure to get the current value of count and print it out. Here I use C++ syntax. So let me quickly go through it. Increase procedure adds 1 to count. Decrease procedure subtracts 1 from the count. Get data procedure returns the value of count. So here we have an infinite loop. In each iteration, we call increase to add 1 to the counter, and then calls get data, which returns the counter value and then print it out. So please answer my question. Is the printed value the one just updated? In other words, suppose the current value of count is 3. So I call increase here, making the counter value 4. Now I call get data. Is the returned value 4? Think about it. Please pause for a while. Answer this question. Is the print value the one just updated? Okay. I hope you figured it out. The answer is no. Always think about this. I always encourage you to have a strong concurrent mind rather than thinking in a sequential way. Now let's analyze why. Suppose you and I are running, I run the increment, you run the decrement, okay? So you run the decrement and get a value. So now I call increase, change the current value 3 to 4. Then I exit the monitor. While I am increasing the value of count, you may call inc.decrease. So we don't know the scheduling policy. So after I increase the value of count from 3 to 4, I exit. And you are the only one waiting to enter because you call decrease. So the monitor, even though I may call get data so fast, so that could cause you who calls decrease and me calling get data. Both of us are competing to get into the mutually exclusive monitor. Who will be successful? Well, nobody knows. If I am successful, the value returned would be 4. If you are successful, I wait outside. So if you are successful, you enter the monitor. Subtract 1 from count, making the value count 3. And then you exit the monitor. I enter the monitor through get data. What I get? 3. The value is just updated. So here, be aware of this. Okay? So even though I write a program in 2 statements, it's very likely between the call to increase and the call to get data, someone may cut it doing something inside the monitor. Usually rather unpredictable. Then the next important concept is condition variables. So mutual exclusion is very easy with monitors. You don't need to worry about mutex lock. You just call a procedure. If you are successful entering the monitor, then mutual exclusion is guaranteed. So while a process is executing in a monitor, it may have to wait until an event occurs. For an example, suppose I call a procedure and enters the monitor. While I am working inside the monitor, I find out I have to wait until the value of count to become 0. Then what if there is no mechanism for me to wait for the value of count to become 0? The monitor construct is useless. Therefore, the event corresponding to the variable count being 0 is something we need to wait upon. So a programmer can define events. Each event is conceptually represented by a condition variable. A condition variable, or sometimes we just call it a condition. A condition variable has a private waiting list or a waiting set, and two public methods, signal and wait. So just a reminder, a condition variable has no value. It has two private methods, two public methods, signal and wait. It has a waiting list. You would better consider it as a set. When we talk about waiting, there's no guarantee the release order would be the same as a request order. Always remember, condition variables have no value and cannot be modified. A condition variable is simply to be used to represent an event. You wait on that event and released from that event. There's no value or memory loss. So condition wait, that is the wait method of a condition variable, goes as follows. Let me call CV as a condition variable. The use of the method signal and wait on CV are variable name, condition variable name, CV.signal, and CV.wait. Now, another important things for you to remember. We are talking about the classical monitor. So condition variables and a condition wait and condition signal can only be used in a monitor. Later on, when we talk about threat manager, you could declare as many condition variables in a monitor. The scope of a condition variable is just within the monitor. Outside of the monitor, the type condition variable is not available. So now, let's talk about wait. The wait method is so simple. A process that executes a condition wait blocks immediately a process inside a monitor executes a condition wait. It waits immediately, and that process will be put into the waiting list of that condition variable. That is, that process is no more executing in the monitor, so the monitor becomes empty. So as you can see, the semantics of a monitor is rather complex. It requires you to understand fully in order to program monitors properly. Once you are used to that, you feel that the use of monitors probably much easier than the use of semaphores. Now, let me quickly go through the third bullet. When a process executing in a monitor execute a condition wait, that process blocks immediately. No question asked. You call wait, you are blocked. So this blocked process will be put into the waiting list of that condition variable. Remember, a condition variable has no value, but it has a private waiting list. So because the executing process calls a condition wait, it is put into condition, that condition variable's waiting list. Therefore, that process is no more executing in a monitor. As a result, the monitor becomes empty. There is no process executing inside the monitor. So what is the consequence? The consequence is simple. Because the monitor now is empty, no one executing there, so the monitor mechanism will find out whether there are other processes waiting outside. If there are someone waiting outside, one process or one thread will be allowed to enter the monitor. Always recall this. This is exactly the same as critical condition. So the key word here is a process executes a condition wait, blocks immediately, and put into the waiting list of that condition variable. Then the monitor becomes empty. Someone is allowed to get in. The next thing is condition signal. So condition wait is used for a thread or a process to wait on an event. Remember, condition variables represent events. So if that event is not there, we execute a condition event, condition wait, representing I'm going to wait on that event. On the other hand, condition signal is used to indicate an event has happened. So if there are processes waiting on the signal, the condition variable, one of them will be released. So when a process executes a condition signal, then if the condition variable has someone waiting, one of them will be released. And what if there's no waiting process waiting on that condition variable? Well, this signal is lost as if it never happens. So these two are very different from what you have learned from semaphores. A semaphore uses a counter to keep track how many threads are blocked inside a semaphore. But condition variable has no such thing. It has no values. In other words, it's memoryless. Therefore, when you execute a condition signal, if someone is there, one of them will be released. We never even count how many are there. And if the condition variable is signaled and no one is there, that signal is gone, as if it never happened. So hope you remember this. Never ever use the concept of semaphore for the use of condition variables. Now, we have a problem. Remember, we talk about it. A process causes an event to happen. So that process executes a condition signal. And if someone is waiting, of course, the process that executes the condition signal, it means that process is executing in the monitor, right? Now, if that condition variable has someone waiting, that someone will be released. Did you see something odd here? If a process is released from a condition variable, that process is running in a condition, is running in the monitor. As a result, the process executes a condition signal, and that the process released from the signaled condition variable are running in the monitor at the same time. This violates the mutual exclusion property of a monitor. Therefore, something has to be done in order to fix this problem. If it quickly goes red, a process executing in a monitor, for some reason, that process causes an event to happen. So that process executes a condition signal. And if someone is waiting on that condition variable, someone will be released. So once that process is released from the condition variable, that process would be executing in the monitor. Therefore, the signaling process and the released process are running at the same time in the monitor. This violates the mutual exclusion requirement. Therefore, something has to be done to resolve this problem. So we have two types of monitors currently being used in many systems. So after signal, the released process and the signaling process may be executing in the monitor at the same time. To resolve this, there are two approaches. The first one was proposed by Tony Hoare, we call it Hoare type. The second one is Mesa type, proposed by Lamson and Riddell. So the Hoare type monitor suggests that the release process takes the monitor and the signaling process waits somewhere. For an example, you came to the monitor and found out the counter value is not zero. The event you wish to wait was the counter value being zero. Now, because the counter value is not zero, you block yourself by waiting on a condition variable. So the monitor is empty. Some other processes could run in the monitor. And then sometime later, I call the monitor procedure and enters monitor after doing some works. I make the counter value zero. So I cause the event corresponding to the counter being zero to happen. Therefore, I signal the condition variable corresponding to counter being zero. So you are released. So the Hoare type means that because you have been waiting for that event probably for quite some time, the priority should be given to you, the one who has been waiting for there. But the monitor only allows one process to run. Therefore, I, the one who caused the event to happen, will be pushed out of the monitor and waits somewhere. So simply put, under Hoare type, the signaling process would be pushed outside the monitor, wait somewhere, and the release process takes the monitor and continue its execution. So the Hoare type gives the priority to the released one. The Mesa type is exactly the opposite. Under Mesa type, the signaling process has the priority. In other words, the released process will be removed from the waiting list of a condition variable and pushed outside of the monitor and waits somewhere. In this way, the signaling process continues to use the monitor. This is also used in Java. So a quick recap. When a signal to a condition variable happens, and if someone is waiting there, one thread or one process will be released. Then we have conflict because two processes are running inside a monitor. So one of them must leave the monitor immediately before the other can execute. The Hoare type gives the priority to the released one, and the signaling one will be pushed outside of the monitor. The opposite would be the Mesa type. It allows the signaling process to continue to use the monitor, and that the signal one, the released one, will be taken out of the condition variable and moves outside of the monitor. So under Hoare type, the signaling process waits somewhere. Under the Mesa type, the release process waits somewhere. So this is these are the two types of monitor you have to remember. So when you use a system that supports monitor, the first thing you have to do is figuring out which type of that system support is, the Hoare type or a Mesa type. Because the way of writing programs under Hoare type is different from the way of writing programs, monitor programs, under the Mesa type. So given these concepts, we need to understand what does that mean by waiting somewhere. Under the Hoare type, the signaling process waits somewhere. Under the Mesa type, the release process waits somewhere. You may consider there is a waiting bench for these processes to wait. Notice here, under the Hoare type, the signaling process is kicked out of the monitor. Under the Mesa type, the release process is kicked out of the monitor. So this kicked out process must find a place to wait. Let's abstractly call this waiting place a waiting bench. So each process that involves in the monitor call may be in one of these four states. The first one is active, and this is obvious, the one executing in a monitor. The second one is entering. A process is in the entering state if it's blocked by the monitor. It calls the monitor procedure, but someone is already inside the monitor, so that process is blocked outside of the monitor. So this is entering. The third state is waiting. This means those processes are waiting on a condition variable. And the last one, inactive. Those processes waiting on the waiting bench are referred to as inactive. It was active because they want to wait due to the differences between the Hoare type and Mesa type. When a signal happens, one of these processes must be moved outside of the monitor and waits somewhere. They become inactive. Sometimes these inactive process may also refer to as re-entering process. Let's take a look at why. Now we still have our monitor, we have constructor here, and we have a set of monitor procedure here. Now we have condition variables. Each variable may have some waiting list. Look at it, even though I put it as a linked list, it does not have to be first in, first out. It could be random order. So under the Hoare type monitor, a signaling process would be kicked out of the monitor. Under the Mesa monitor, the released process would be kicked out of the monitor. So they are all waiting outside of the monitor. So the process waiting outside of the monitor are either the entering thread, they call the monitor procedure, but at that moment, someone is running inside the monitor. They are forced to wait outside of the monitor. Or the second group is the group of inactive processes or re-entry process. They were inside the monitor, but due to the fact that either in a Hoare type or a Mesa type, they cannot execute continually inside the monitor. They are forced to get outside. We call them re-entry because they were in the monitor. So they are moved outside because they have to yield the monitor to the other party. Next time, when the monitor will become available, they will re-enter the monitor. As you can see, the syntax of a monitor is rather simple, but the semantics would require you to remember a whole lot of things. So the major difference is here. The way for you to wait on a condition variable. So let's say we have a condition variable. Let me call it until happen, a condition variable. So under Hoare type, if the event, whatever it is, say counter being 0 or something is equal to something else, so as long as the event is not there, we wait on the condition variable until happen. So we call until happen dot wait. Now, if someone has caused the event to happen, and you are released from here, under the Hoare type, the one who made the event to happen and release you from here, that someone is gone outside of the monitor immediately, and you, the release one, immediately get the monitor. So the event is still there. So it's also something like a passing the baton concept. The signaling process has the baton. It caused the event to happen. Immediately, it passed the baton to you, allows you to run. And in that one, the previous leg get outside the monitor immediately. So you get your baton and run. But for the Mesa type, it's different. Look here. This is typical case, not always. Under Hoare type, I use if. But under Mesa type here, I use a while. Why? Let's take a look at it. Now, if the event is not there, I wait for sure. But what if I am released from until happen? Can I assume that the event is still there? Think about it. If your answer this question is no, we are not sure, you are right. Remember, under a Mesa type, when a signal happens, the signaling process continues. The release process will be taken out of the waiting list and pushed outside of the monitor and wait somewhere, the re-entry queue. Many systems does not distinguish whether a process outside of the monitor is in the entering state or in a re-entry stage. But that is not so essential here. So as long as we have a Mesa type, a signal happens, I am released. Because I am released, and because this is a Mesa monitor, I will be pushed outside of the monitor. The one who signal me continue to use the monitor. And then that one exits the monitor, so that the monitor becomes empty. The monitor mechanism is allowed to pick a process to enter. That process could be a process in the entering state, or that process could be in the inactive or re-entering state. What if the next process to be selected into the monitor is not me? Probably a third person. That third person could get into the monitor and mess around, making the event change to something else. So by the time I am able to get into the monitor again, this event may not be there at all. Therefore, this is why we have a while statement here. When I am released, I may not get the monitor immediately. By the time I am back, the event could have been changed by someone else. So I have to come back and check to see whether the event is still there or not. This is the reason for the Hoare type, we use if. For the Mesa type, we use while. This is extremely important. So in the next lecture, we will use Hoare type mainly to explain a few examples. We also explain with some simple example telling you that if we write a solution to a problem based on the Hoare type, and if the system is not the Hoare type, the system supports Mesa type, your program could screw up immediately, getting you unpredictable result. So let me stop here for this lecture. See you next lecture, which will explain to you several classical examples using monitors. Goodbye. See you next time.